Right, okay, so this video, in this video, what we're going to do is we're going to use virtual radiography, ProjectionVR, to undertake an experiment based on this paper. So we found this original research article in the literature, and my second year students at the university were looking into ways in which they could optimize radiographic techniques. One of the ways that interested them was the use of copper filters. So the idea was we took this paper and we read it, and we looked at how they'd done the experiment. They were looking at abdominal x-rays, and so we reproduced that as best we could using ProjectionVR. So we took some abdominal x-rays, we took some dose measurements, we took some image quality measurements, and we reproduced this paper. So I'm going to show you now how that was done as an example of the sort of thing you can use ProjectionVR for in some of the more technical aspects of the course. Okay, so what we're doing, guys, is we're going to x-ray something, and we've got some constants here. We're going to x-ray a male phantom at a source image distance of 120 centimeters, and we're going to change the copper filtration values. We're going to keep the KVP constant, and we're going to change the MAS to get a constant exposure index. Yeah, that needs to be an exposure index, and I think the value we're looking for is 250. And what we're going to do there, we're going to record all our dependent variables. Yeah, and that's what we've got to do in this hour. So what we're going to do then is discharge this female patient and bring up our male patient for an abdomen. So modality work, there's going to pick male patient. Okay, change that to abdomen because I can't be bothered to find one. Abdomen, recumbent, abdomen. So that's all good. So now what we do is we go to floating table, bring the guy in and pop him on the table. Raise the table to working height and put a receptor into the bucky. Yeah, the right marker down here at the bottom. Okay, so the source image distance at the moment is 108, so we need to raise that up to 120, sorry, because that was the standard. That's what one of our constants. And what I'll do is I'll just bring that across, because it says that we want collimation to be 35 by 41. So we need to guesstimate that, I'm afraid, because we can actually measure it in the DICOM, micro DICOM, when we just to check that we've got it pretty close. But what I'm doing here is I'm going to open the collimation to 35 and across to 40. 41 is slightly in from 43, isn't it? So that'll do, something like that. You happy with that?
Yeah.
Thank you. Okay, so now one good, if you notice, look, it doesn't tell us what the centering point should be, which is a constant they should really tell us. So shall we put that in? Do you know what is the centering point? Because you're going to have to write this in your method, yeah, to make it reproducible. And it's something you can criticize the paper for, because it hasn't given all the information that you need to be able to reproduce the paper.
It's the belly button, so you feel the iliac crest, and then I'm doing my hand movements, but then you put your two thumbs towards the middle, and then that's the centering point as to where you need to center for an abdomen.
Thank you, Claire. So your centering point is in the midline at the level of the iliac crest, yeah? That is perfectly adequate centering point, I would say. Good. So what else do we need to do? We've set it up for the exposure. We've got the patient there ready. We'll have to do a test exposure now to see if we've got everything right. So our test exposure is going to look for 80 kV, no copper filtration, and we're going to set a tube charge to hopefully get an exposure index of 250. Yeah, that's the first exposure we're going to do. So I don't know what will be a reasonable abdomen exposure. Do you guys know an abdomen exposure?
I've got 77 and 20 MAS.
Right, okay, yeah, so we'll drop this down to 20 then. 80 is near 77. We can't change that. We have to have it at 80. By the way, I can't get to 80. It's either 79 or 81. So take your pick. We'll go 81, shall we? Right, I'm hovering over the exposed button. We're going to have a look at this and see what's what. Okay, what do you think? We've probably got a bit too much Symphon here, haven't we? We could get a bit more abdomen on. So what I'm going to do is I'm going to position him down a bit so we get just the top of the Symphon. Is that okay for you? Do you agree?
Yeah.
Yeah. Okay, so I'm just going to move the table down a little bit and make sure he's in the midline again. And the other thing to note on that image was we didn't have side-to-side collimation, we only had top to bottom. So if I just go in a little bit side to side, then that should work. Oh, the other thing, the exposure index is 575, right? So that's too much. Now there is something called so basically we need to halve it. The MAS and this are linearly related. So that means that if I want to halve that to get to 250, then I should halve the MAS. So what we'll do is we'll drop this down to 10 and see what happens. Okay, so that worked. Look, we're now at 266, which is pretty close to 250. My tweak with the sideways collimation didn't work. We've still not got the collimation in. But we have now got a nice little, just the top of the Symphon, which is much better. You agree?
Yeah.
Yes.
So I'm going to drop this just a little bit more and see if we get 4 collimation marks on. Yay! Notice that when you collimate, because you now got a few less pixels in the average, the exposure index has changed a bit. So the exposure index does vary when, depending on collimation as well, but 243. So if I go to 11, just to see. So 268 is 18 over, 243 is 7 under, so 10 is closer to 250, yeah? So I think that's what we should go for, which is 81 and 10. Okay. So that's our first exposure, yeah? It's actually entitled the internal column. So it's taken us a few exposures to get set up, if you like, but the first exposure that worked was exposure 6. So it was our 6th attempt. But now we're all set up. We've got our constants. So we've got a source image distance of 120, male phantom, collimation size. In our tech data, it tells us. So the collimation size, it just tells us at 100, but I think it's close to 35.41. And it's going to be fixed now. We're not going to change it anymore. We're using a 12:1 ratio grid. We'll put that in, 12:1 ratio. We're using an aluminium filter, 3.1 millimeters, which is the standard on the machine. And we've centered in the middle line with the patient. Okay, we better put in the patient position, which is recumbent, or supine, we'll put supine. And we need to put the patient projection in, which is AP. I know everyone would assume an abdomen should be AP, but it's important to make it, you know, anything we've done, we ought to describe really in our methodology. The exposure index we ended up with was 243. So I'm putting that in, but we're going to try and keep it as close to that for the next exposures, right? You all following me so far?
Yeah.
Yeah.
Yep.
Fantastic, fantastic. So what we're going to do now is, as I read it off, can you write these numbers down? So tech data. So the first thing is the entrance surface dose in milligray. So the entrance surface dose for our first exposure was 1.752 milligray. 1.752. Okay, the next dependent variable is dose area product, and the dose area product was 99.59 centigrade centimeters squared. And then dependent variables 3, 4, and 5 we can't do yet, but what we need to do is we need to do the contrast to noise ratio 1. These visual grading scores, you're going to have to do these because we haven't got time to all mull over and look at all the images, and sort of like they need to be blinded. So I need to create a little PowerPoint with these images in which you don't know the order of, and then you need to score them. Do you know what I mean? To get those numbers in the week sometime in the next couple of days. So I'll send you a PowerPoint with these images in, which you won't know which order they're in. Yeah, and then you can score them, and we'll see whether we get some scores. But we can do this objective image quality one, which is the contrast to noise ratio. So we'll do that now. Right, so microdicom. So now in microdicom, I've got group 3 XST Simpson, and I'm now opening the image. So this is our image in microdicom, right? I suggest we draw a 75mm circle over the psoas. If I can get 75, come on. I'll do 74.68. So we're drawing a 75mm circle over the psoas. And then we'll, just for ease of describing where it is, we'll put a 75mm area over the head of femur on the left side. Okay, so we've got our background and our object. The reason why I'm doing that is because I can't discern a kidney shape or a soft tissue shape in there. It's all a bit of a mess, isn't it? So we've got two areas distinct. One is a soft tissue and one is a bone. So we've got two distinct differences of tissues, and we can look at those two separately. So the soft tissue background is the psoas. So can somebody write this down, or all of you write this down as your mean object pixel value? Sorry, mean background pixel value. So this is 2006. And the standard deviation background is 20. Now the mean object, head of femur, is 2283.58, so that's 2284. And the standard deviation object is 30.30, just 30. Have you got those?
Yeah.
Right, I'm going to save those because when we put a new image in, I'm going to be able to paste them in exactly the same location. But in your methodology, you're going to have to describe the location of the regions of interest. Okay, so can someone read them back to me? So the M-obj, what did you write for that?
2006.
schema there, just so that I remember.
No, I think it's the 2284.
84, yeah.
2284. Perfect. See, we need teamwork, don't we? Mean background.
That's the 2006.
Yeah. So this is SOAS. And the standard deviation background.
30. Oh, sorry, background's 20.
20. Happy? So that gives us a contrast noise ratio of 13.9. Okay. Fantastic. Let's go and do another exposure. So now what we need to do here is need to bring a copper filter in, 0.1 millimeter of aluminium. So doing that here now, this is our independent variable. So we're going to, now we don't know how much we're going to have to increase the MAS yet. So we're going to have to do a test exposure, see what effect that has on our MAS, and then raise the MAS to get the same exposure index. Okay. So adding the copper filter has dropped our exposure index from 243 to 228. So what we need to do is up our MAS to correct for that. So if I go up to 11, hit the exposure. We're at 251, so that's pretty good. So we now know our tube charge should be 11, and our exposure index is 251. You happy with that? What we've done is we've changed our tube charge to correct for the added filtration, so that we get the same exposure index, or very similar anyway. Right. Okay. So let's go to Tech Data tab. So guys, can you write, this is our exposure. Which exposure is this? This is exposure 9. Exposure 9. So our entrance surface dose is 0.935. Write that down, please. And our DAP is 52.61. Fantastic. Now let's go to microdicom and exposure 9. Load that. List the regions of interest into the same exact spots. So can you write these down, please? So our mean background is 2012. Our standard deviation background is 21. Round that up to 21. Our mean object is 2,291, but it needs rounding up to 2,292 because it's 0.51, I think, there. And our standard deviation object is 31. Have you got that?
Sorry, what was the deviation? Object deviation?
31.
31, thank you.
Okay, what I've just thought about actually is we need to print screen this because you might want to use this image in your poster to show how you did the regions of interest. So I'm going to print screen this and then just save it on. Okay, so file, save as, and I'm going to put it in your folder, group 2, group 3. Yeah, so that's good. Because you might want a picture in your methodology. It's always good to have pictures in posters rather than lots and lots of texts, if you see what I mean. Right, so that's good. So let's write those down in here. So the mean object, what did you get there for that?
2292.
So this is the head of female one, 292.
2292.
2292.
Yeah.
Perfect. Thank you. And the mean background, SOAS?
2012.
And the standard deviation background?
21.
Of truth. So the image quality is pretty similar. I'll just change the format of that to one decimal place because it's a bit. So it was 13.9 and now it's 13.3. So it hasn't dropped much. Let's do the dose values because you wrote those down. So what was the entrance surface dose for our first exposure?
1.752.
1.752. And what was the entrance surface dose for the one we've just done?
251. Oh no, sorry, 935.
That 0.9.
0 point.
Yeah.
So that's halved. So the image quality stayed the same and the radiation dose is halved. That's quite interesting. Okay, so dependent variable 2, dose area product, what have you got for that?
99.59.
99.59. And for the second exposure?
52.61.
So that's halved as well. Actually, it's not the same units though, is it? Instead of microgray, it's centigrade. So we'll change it to centigrade in there. Make sure you make that point when you compare this to the paper in your discussion. Because in your poster, you're going to have to compare your results to the paper's results. Right. So now we've got to go to 0.2 mil of copper. Yeah. So are you all following what we're doing?
Yeah.
Yeah.
Brilliant. So I'm now adding 0.2 mil of copper. Again, we don't know what the effect that'll have. So we have to make a test exposure and then change our MAS accordingly. So expose. Okay. So it's gone down to 202. So we need to up it by about 25%. So I'm going to go up by 25%, which would be 2.5. So if I go to something like 14, that might work. Let's give it a go. Hover over. It's 258. So I'll just tap it 1 just to see what happens. The 258 is the best one. So we'll use the 14 exposure 14. Okay, so this is exposure 13, E13. Now we used 14 MAS and we got an exposure index of 258. Right, go to tech data, read off the numbers. So you write these down for me, please. So the entrance surface dose was 0.754. The dose area product was 42.29. And we'll do the microdicom, contrast noise ratio. So open up exposure 14. Hasn't landed exposure 14. Oh, it's exposure 13. I got that wrong. Open that up. Paste regions of interest. Okay, so mean background is 2010, well, 2011, because it would be rounded up to 2011. Standard deviation will be 21 when it's rounded up. So that's background standard deviation. Got that recorded. And then the mean object is 22.73, which would be rounded up to 74. and the standard deviation is 31. Got them?
Yeah.
Okay, let's read them off. So, first one, dose, milligray. What did you have for entrance surface dose?
0.754.
And for dose area product?
42.29.
And for mean object?
2274.
And mean background?
2011.
And standard deviation?
21.
Standard deviation background, 21?
Yeah.
12.5. Okay, so the image quality is dropping a little, so that's quite interesting. Let's draw a graph of that. So what I would do now is create tables and graphs. So we've collected our 3 exposures. So the independent variable is the copper filter. So we copy that table, we put it into a new sheet and paste it in there. And I'm going to, so that's my independent variable. Okay, and I'm going to paste it twice because I want 2 tables, because we've got 2 independent variables. Sorry, 2 dependent variables. I've got image quality and dose as our independent variables. Okay, hang on with me because you'll see what I'm doing in a minute. Okay, because you need some tables and some graphs for your results section. Yeah, so we're creating them now. So I'm going to go back to the sheet 1 now. Ignoring all those, I'm going up to the dependent variables. So the first dependent variable we've got is dose. And I'm just going to do the entrance surface dose for now. So that's going to go here. And bring that over there. Okay, and then the second dependent variable that we want is the image quality. This is the image quality value. Go to C2. That's my image quality. I'll change those because that's crazy. Change that to format, number format. Change that to 1 decimal place. That's better. Okay, so now what I'm going to do is I'm going to make these into a table. I'm going to center them, center alignment. I'm going to make a grid around them, and I'm going to make those bold. And then similarly here, I'm going to center them up, draw a grid around them, and make them bold. So we've got our tables, yeah, for inclusion in your poster. That was easy. Now, what we can do now is do a graph, so that shows trends. So just highlight the dose, the data, insert, graph. That is the trend line for your dose. And now we do the same for image quality. Insert. So here, enable editing. I can change format axis. Then I can change this to minimum. In scientific experiments, you should always have the minimum as 0. Yeah, because watch what happens with this trend line when I change that to 0. Do you see how it used to look like it was a really significant drop in image quality, but now it looks like it's hardly changed?
Yes, Phil.
Yeah.
Thank you.
Yeah.
Do you see how, because that one's 0, and if this one was left when it wasn't 0, do you see what I mean? It would look like, well, as the dose dropped, so did the image quality, wouldn't it? That would have been the conclusion. But now they're both set at the same axis. You can see that as the image quality drops, as the dose drops quite significantly, the image quality stays pretty much the same.
Yeah.
And you can see optimum, right, is like mother bear's porridge. And you know, you've got baby bear's porridge, mother bear's porridge, and daddy bear's porridge. Can you explain how that story goes?
Wasn't it like when it was the porridge? It was like, Mummy bear's porridge is too cold, Daddy bear's porridge is too hot, but baby bear's porridge is just right.
Yeah, that's it.
So that is optimization in a nutshell, right? So which is the correct amount of copper to use? The answer is it's the one that is just right. You know, so 0, no copper is too high a dose. Yeah, 0.2 mil of copper is too low an image quality. 0.1 millimeter of copper is just right. So it's better perhaps just to have one set of dose data and one set of image quality scores, because you've got only a small amount of space here in this poster. And also, when you read the paper, was it confusing?
Just waffled on.
Yeah. And this, basically, the experiment's far simpler than they make it seem. You know, we've given this a few hours of our time, haven't we? We did an hour last week where we just looked at the paper and deconstructed the experiment and came up with the spreadsheet. And we've spent 45 minutes today doing the experiment and collecting the data. So it wasn't that complicated, really. And it'd probably take another hour to do the image quality scores and collate all that data. So in 3 hours, you could have actually created the data set to do this and then you write it up a few days, take a couple of days to write up the paper and submit it to a journal. So I'm hoping the whole idea here is that we've demystified the process, and you pretty much all the papers you're going to be reading, they're all as simple as this, really.